Let f be bounded and non-decreasing function on closed interval ab, and let P be the partition of closed interval AB, and there exists Ti which is belonging to this xi minus 1 xi closed interval. Then it is a new thing which is defined over here, which is a sum. SPF alpha is equal to summation f of Ti into delta alpha I, where I going from 1 to n. So it is a sum of all these. Second, if f is Riemann integral on closed interval AB, for given epsilon positive, there exists a partition P such that if I take the mod of SPF alpha, that is the sum, minus integral of f d alpha, then this mod will be strictly less than epsilon. And you can also suppose to be as A, this integral of f of d alpha. I'm going to use these results in the proof, alright? Third note is, if your f is sum of the functions or the difference of the functions, anything, then if you take the mod of SP f1 plus f2 alpha minus integral of a to b f1 d alpha plus a to b f2 d alpha, this mod will be strictly less than epsilon. If this happens, but epsilon was arbitrary, if this result is true, then this f1 plus f2, this is Riemann integral on closed interval AB, and integration of the sum is equal to integral of f1 plus integral of f2, which means if I required to prove this result, then I have to reach this, right? In the proof, I have to reach at this. So for reaching this, I'm going to use this result and this result from the very start. The theorem is, if f1, f2 is a Riemann integral on closed interval AB, then its difference is also Riemann integral on closed interval AB, and a to b integral f1 minus f2 d alpha is equal to a to b f1 d alpha minus a to b f2 d alpha. So let's start with the proof. Now for any given partition P, x0, x1, x2 up to xn of closed interval AB, we have SP f1 minus f2 alpha. This is equal to, yes, because it is your sum, so it is equal to summation I going from 1 to n. I'm going to use the result for the summation. Then f1 minus f2, because my function f is f1 minus f2. So here in place of f, I have used f1 minus f2 into delta alpha I, right? So this is equal to summation I going from 1 to n. What this will equal to? It is f1 ti into delta alpha I, summation I going from 1 to n, f2 ti delta alpha I. This difference is dependent upon this ti, right? And delta alpha I is multiplied with this function. Alright, so this is nothing but your SP f1 alpha according to the definition, and this is SP f2 alpha. Alright, now since f1 and f2 is Riemann integral, this is given to us. So therefore, for a given epsilon positive, there exist partitions P1 subset of P and P2 subset of P. I'm going to use this partition P1 for F1 and P2 for F2 of closed interval AB, such that, again, the second result I'm going to use over here, such that if I take the mod of SP first for F1 function, F1 alpha minus integral a to b f1 d alpha, this mod is less than epsilon by 2. Let me take epsilon by 2, and mod of SP f2 alpha minus a to b integral f2 d alpha, this mod is less than epsilon by 2. Okay, now again, P1 union P2 is also a partition of closed interval AB, right? Such that P1 union P2 is also the subset of P. And we have S of P f1 minus f2 alpha minus integral a to b f1 d alpha minus integral a to b f2 d alpha. Remember, what is required to prove in the theorem, take that as your a. S of p f1 minus f2 alpha minus this whole a, which you need to prove. Just take that a over here, right? You have to take the difference with that a and take the mode. Okay, so let's solve this. So this is equal to mod of S p f1 alpha minus S p f2 alpha, right, minus a to b f1 d alpha plus a to b f2 d alpha, right? Fine. All right. Now taking this sp1 alpha with this f1 d alpha. So this is equal to s p f1 alpha minus integral a to b f1 d alpha minus then s p f2 alpha minus integral a to b f2 d alpha mode. From here, let me write down here, this is your star. This mode is less than epsilon by 2. This mode is less than epsilon by 2. Right? Okay, if you separate this mode, do you know that this difference is equal to actually the mode of this plus mode of this, right? Which is less than, this first mode is less than epsilon by 2 plus second mode is less than epsilon by 2, which is actually equal to epsilon from star or using star. Is it clear? All right. So that is what we have got, that SP f1 minus f2 alpha minus this whole difference is strictly less than epsilon. But epsilon was arbitrary. So from the result, the third result, we have reached over here, right? So from here we can write, therefore f1 minus f2 is Riemann integral on closed interval AB, and this integral a to b f1 minus f2, this one, this is equal to this. Hence proof. Right? So I have to reach the result up to here. Then by using the third result, I will get this, which we have to prove. Okay. There are other ways also to prove this theorem, but that were very lengthy. This is a very small and easiest way to use the summation formula, right? That is SPFL formulas, right? Thank you.